So we discussed the characterization theorem for MSNE. Now let us look at how we can use that result to develop an algorithm to find the MSNE. So let us consider the normal form game, which is represented by a set of players N, their strategy is SI, and their utility is given by UIs. Now the most straightforward and you can call it a brute force way of finding the mixed strategy Nash equilibrium is by iterating over all the supports. You have to find out all possible subsets, non-empty subsets of S1. So the number would be 2 to the power cardinality of S1 minus 1. So this minus 1 is coming because you are just excluding the null set. And similarly for others. So this is actually an exponential number. If the number of players and their strategies are quite large, this number k could be a very large number. But anyway, so we are going, so this is a finite number, we are going to iterate over all this. So let us look at this, the support profile. So one specific support profile, and there will be k such support profiles. So this support profile is x1 Cartesian product with x2 to xn. So where all these xi's are subsets of capital SI. Now we know there are two conditions of the which says it is necessary and sufficient for mixed strategy Nash equilibrium, and we are just using those two conditions to write down the following. So first we are writing down, let's say, a wi, some variable which is going to be constant for a particular player, and we know that this is going to be the equal for the utility of player I when the player I is choosing a pure strategy SI and the other players are choosing a mixed strategy sigma minus I, and this SI is within that support. So we are just writing that down explicitly. So you can see that this whole thing is nothing but an expanded view of SI sigma minus I. Right? Then you can actually write it down because all the sigma minus I star are independent, sigma minus i's are independent. So you can write them as a product of those individual probabilities, and then you multiply that with the utility of agent I at that strategy profile, pure strategy profile SIS minus I, and then you take the sum over all S minus I's, all the strategy profile of the other agents. This must hold, this must be equal for all the strategies which are in the support. So currently we are assuming that Xi is the support for player I. And this Wi might change for different agents, but that should be same for all the strategies in the support of that player. So this is essentially rewriting condition 1. We also know that this value, what you get as Wi, is going to be at least as much as the utility of some SI prime. So if you just want to distinguish this, maybe you can just put a SI prime where all these SI primes are actually outside the support. So that's all we have, and this is essentially the condition 2 of that characterization theorem. And the rest of the inequalities or conditions are essentially feasibility conditions. So you have all these sigma i's, sigma j's they are probability distribution. So sigma j is a probability distribution, so they must be non-negative and they should sum to 1. These are the two conditions that you have to satisfy for all the players. So this is essentially the algorithm. Now this is a feasibility program. You'll have to just solve. If there exists some solution for, you iterate over all the strategy profiles, x1 cross x2 to xn, and whenever you find a solution to this feasibility program, you output that as a mixed strategy Nash equilibrium. There could be multiple mixed strategy Nash equilibrium. Yeah, so we'll see that whether this the feasibility program will always return sumptive values or not. Okay, so this feasibility program has these variables. Wi's are the variables, and sigma j sj for all sj's belonging to capital Sj and j in n. These are the two set of variables in this feasibility program. So one thing, so this is kind of writing down all possible things and trying to find a solution. The question is, can we find a better algorithm than this? So you can see that this is not going to be a linear program. So because the variables are sigma j's and they are getting multiplied. So as long as there are more than two players, this is not going to be a linear equation. For two players, yes, this is going to be a linear equation. But for anything beyond n equal to 2, this is not a linear program. The answer to the question that we have just asked, whether there exists any algorithm which can do a little smarter than this, the answer to that is actually negative. So there does not exist any polynomial time algorithm for finding the mixed strategy Nash equilibrium. And I will quote one result which you can look up. So the problem of finding an MSNE is what is known as a polynomial parity argument on directed graphs complete. So PPAD complete. So this is also a very important and landmark result when we are talking about the complexity of finding a Nash equilibrium. The title of the paper is actually The Complexity of Computing a Nash Equilibrium. It came about in 2009, and this was by Daskalakis, Goldberg, and Papadimitriou. So it says that you actually do not hope to have a much smarter algorithm than this. To find the MSNE in a general game is actually hard. Let us now look at the relationship of MSNE with dominance. We have already seen the relationship between dominance and PSNE and several other things, several other notions. So let us look at the dominance and its relation with the new concept that we have just looked at. Now, what is the advantage of having a dominated strategy? We have seen that we can just assume that the players are rational, and rational players do not play dominated strategies. So you can eliminate some of those strategies in order to find out what is the Nash equilibrium of that game. We are in a little general situation here. We have the players now have a strategy which is not necessarily pure. They can actually mix their strategies. So can you tell me, maybe pause the video for a while and think about, in this game on the right, do there exist any dominated strategy? So if you just go by the pure strategies, you will see that there does not exist any dominated strategy, a strategy which is dominated by another pure strategy. But here we are making this point that domination can also be via a mixed strategy. So now if you look at this carefully and try to find out, do there exist any strategy which can be dominated by a mixed strategy, a combination, probabilistic combination of other strategies? And the answer is yes. You can actually do a probability half and probability half on T and M for player 1, and you can see that that is going to give you 2.5, which is the utility for this mixed strategy, and this is 1 and 3, which is 4. So both these numbers are actually larger than the corresponding numbers here. So even though there does not exist any pure strategy which dominates the pure strategy B is actually dominated by a mixed strategy for player 1, which is half, a half, and 0. So this is an interesting point, that dominated strategy you can also extend for mixed strategies. Now, whenever the players have the choice of playing mixed strategies, you can use the same argument of rationality, that if the player knows that there exists another strategy, another mixed strategy, which is going to give you better utility at every state of the game, no matter whatever the strategy being chosen by the other player, that dominated strategy can be removed without loss of optimality of this game. Okay. So we have seen that weak dominated strategy removal can actually remove equilibrium. But when we are removing strictly dominated strategies, we have a theorem, and I'm not going to prove this theorem. The proof is available in the book. but the final observation from this theorem is important, that if you have a pure strategy SI that is strictly dominated by a mixed strategy sigma I, then in every mixed strategy Nash equilibrium of that game, SI is chosen with probability 0. So there is no harm if you remove that strategy from the strategy set of player I. One of the most crucial questions of mixed strategy Nash equilibrium is about its existence. We have seen the previous notions of strongly dominant strategy, weakly dominant strategy equilibrium, then pure strategy Nash equilibrium, and we have found that there could be game examples where this might not exist. Now, what is the answer for MSNE? So in this case, we are going to consider that this is only a finite game. So by finite game, we mean that the number of players and their strategies, the set of strategies, are all finite. So for this finite games, there is a landmark result. Again, this is one of the most famous results, early results of game theory, and this is due to John Nash, which says that every finite game has a mixed Nash equilibrium. So this actually demystifies the existence question. The mixed strategy Nash equilibrium finally gives you a guaranteed existence. So we are not going to prove it, even though the proof is actually quite simple once you know the results. Instead, what I'll do is I'll post a note which has the complete proof, and I would suggest you to read through that. In order to read that note, there are certain notions which are required in order to understand that proof. So in this, in the remaining time of this module, I'm going to explain to you, just to make this complete, that what are those notions and what is the result that we need to prove, to understand that proof. Okay, so it requires the following notions. So I believe everybody knows what is a convex set is. So we call a set to be convex if you pick any two numbers, any two elements of that set, and take a convex combination of that. So here we are always considering subsets of R to the power n. Of course, this definition will be more general for general classes of convexity. But let us only restrict our attention to real numbers, to real spaces. Now, if you pick any number between 0 and 1 and take this combination, which is also called the convex combination of these two values. So this is actually a little wrong. So this will be lambda x plus 1 minus lambda times y. So what it means that suppose you have a set, and you have one point x here and one point y here, then the whole line that you connect, that must live in this set. In this example that I have just drawn, it is not a convex set because there are some points by taking this kind of a convex combination that can live outside the set. So the convex sets should always have some shapes where if you join any 2 points, the whole line should live within that set. Okay. So we call a set to be closed if it contains all its limit points. So what does this mean? So what is a limit point? So these are points whose every neighborhood contains a point in S. So imagine, for instance, this example. So you have a real line segment, and you are considering all the points from 0 till 1, but not including 1. So what it means that if you look at the point 1, let's say this is the 1 point, and you draw an arbitrary small radius circle around it, ball around it, and the width of this ball, or the radius of this ball, is epsilon, and that has to be positive. That is what is meant by a neighborhood. So the epsilon cannot be equal to 0. Then if you look at that, there must exist some element from this set, from this 0, 1 open set that lives within that interval. So if you draw any point sitting at 1 and take no matter whatever small radius you take, there should always be some points which is living inside inside this set of 0, 1, close at 0 and open at 1. So then we will call this point 1 to be a limit point. But in this set 0, 1 open, that 1 is not a member of this set. Therefore, this set is not closed. Right? So the closed set will be something like 0, 1. Right? So where if you take any limit points, that is already in the set itself. You can actually think about multiple unions of such closed sets. They are also closed. So if you take 0, 1 and 2, 3, both are closed sets, and take their union, that is also a closed set. Now the third thing that we will require is boundedness. So boundedness means that if you have a set, let's say an arbitrary sized set, then there must exist some x0 around which you can actually draw a circle. Okay, so again a ball which has some finite radius, so a radius which is living within zero and infinity. So finite radius, so that all the elements must be within that radius. So all the elements that you can pick from that set, and you take its distance from x0, that point, that distance must be less than r. So in other words, that ball of radius r centered at x0 can completely enclose your set. So then we'll call that set to be bounded. Now you might think about some interplay between this. Why are these things different? So could there be a bounded set but not closed, closed but not bounded, closed and bounded but not convex? You can think about all this. Maybe that will be a good exercise to understand the concepts of all these notions. So compactness in this setting, of course, there is a more general definition of compactness, but for the purpose when we are looking at only sets in the r to the power n, the compactness definition essentially boils down to the set being closed and bounded. So if a set is closed and bounded, we'll call that compact in this context. All right, so now we can actually present the result that we are going to use to prove the Nash theorem. And this theorem is known as Brouwer's fixed point theorem. There are several fixed point theorems, and they have almost the same conclusion, but the conditions change based on what kind of fixed point theorem they are. So this theorem says that if you take a set which is a subset of r to the n, and that is convex and compact, and if you consider a function t which is mapping this set into itself, so it is taking this set S and mapping it to itself, the condition is that this function that you are picking is a continuous function. So if this conditions hold, then the Brouwer's fixed point theorem says that the function t, this continuous function, has a fixed point in S itself. So for fixed point in S, I think that is useful to mention. So it means that there exists some x star in S such that, so what is the fixed point? Fixed point means a point which maps into itself. So just to give you a kind of a feeling of what this means, let me just cast this theorem for one-dimensional function. So let's say Tx, and T is just mapping from the set of real numbers to itself. Or actually, I cannot take real number because that is not convex and compact. So let's say I take, instead of this, I take 0, 1 to 0, 1. So I have on the x-axis the domain, so the domain of this function t, 0 to 1, and the range is also going to be 0 to 1. So this is the thing. Now what a fixed point means is that if the function value crosses this y equal to x line. So imagine a function. So remember that this function has to be a continuous function. It cannot have any jump. So can you ever draw a function which does not touch this line? That is not possible. I mean, that is essentially the thing that is formally stated by this theorem. If you had a function which had a jump, let's say we had up to this value a point and then there was a jump, then you could have skipped this value y equal to x. So but for any continuous function, you can always find that there exists these points tx equal to x, and that is what this theorem is telling about. For any any continuous function which is mapping a convex and compact set into itself, you will always have a fixed point. Let me just point out that the convex and compact set, if you look at the mixed strategies, sigma i's, what are they? So they are some numbers, right? So they actually live in r to the power, let's say the cardinality of si, and also with the additional constraint that if you actually this has to be not only real, it has to be greater than non-negative value, and all those sigma i's, si's, sum over all these si's in capital Si must be equal to 1. Now you can convince yourself that the set of all possible mixed strategies is essentially a convex and compact set. Now we can use this idea to find the fixed point, and we'll have to, so the proof of the Nash theorem essentially carefully constructs this continuous function such that you get the fixed point as your Nash equilibrium, mixed strategy Nash equilibrium.